For the first question on Lab 3, we're basically going to use a workbook exhibit as a prop. Exhibit 1 of Beyond the Numbers 3.14 is on page 265 in the workbook, and instead of answering the two questions that are there, answer these two. First, write out the null and alternative hypotheses in words, then, should the null be rejected, why or why not? As far as the point breakdown for B goes, I think it's pretty easy to anticipate. Half a point for the yes or no, and half a point for the why or why not. Part A, writing out the hypotheses in words, that's a little different, and we're going to go through an example which is on the next slide, which is based on the other exhibit in Beyond the Numbers 3.14. First of all, how the points breakdown is going to work, it's a hypothesis test for a difference. So ultimately, this would probably have fit a little bit better on Lab 4 than Lab 3, but we have covered it already. I think that'll be okay. So it won't be parameter equals some number in the null and parameter some inequality and then some number in the alternative. It'll be a null where it's one parameter equals another parameter, and an alternative where it's one parameter is somehow unequal to another, whether it's a greater than, less than, or not equal to. But it is a hypothesis test for a difference, so there are going to be two groups. Half a point is for the type of number, if we're comparing proportions or comparing means. That's what I mean by the type of number. 1 point is for identifying the populations or groups that are being compared. I suppose that means each population or group would be worth half of a point. Half a point for the specification, as far as writing out the parameter is concerned. Half a point for having the right inequality in the alternative hypothesis, and half a point for having an equality in the null. What I've got on this slide is what you would do to answer the questions on the lab, just applied to Exhibit 2 instead of Exhibit 1. The reason I assigned Exhibit 1 on the lab instead of Exhibit 2 is because Exhibit 2 has a part that's a little murky. It doesn't explain what a numerically superior rating is, in the sense of is higher better or is lower better. I'm going to assume that numerically superior means higher here. That would affect what the alternative hypothesis would look like, because if it was the other way around, then you get the other inequality, you get the opposite direction. But if we're going to do this assuming that numerically superior means higher number, then you'll get what I've got here on this slide. What you should end up with for hypotheses relating to Exhibit 1 won't look exactly like what I've got here, but your hypotheses for Exhibit 1 should look pretty similar to this. And if you follow these as a template, I think what you'll get on your lab for Exhibit 1 will work out okay. What's here for Exhibit 2 is that it's comparing two groups, if you look at what's there on page 266. Two groups or two populations. We have stuttering patients who take pagoclone and stuttering patients who take a placebo. And the type of number being compared is a mean, since we have quantitative data. So that's where a mean is going to make sense. It will be a difference of means, not a difference of proportions, and that may not be the way that it works for Exhibit 1. With writing out the hypotheses, the other things that we're going to need would be the specification, which I suppose here the specification would be numerical rating, and then the equality in the null hypothesis and inequality in the alternative. What you're looking for generally, if you're comparing any kind of medicine or treatment to a placebo, is that you want to see if there's evidence that the medicine or treatment does better than the placebo. If numerically superior means higher, we're looking for evidence of a higher average numerical rating for the pagoclone group, because that would be evidence that pagoclone actually does something. What I've got here on the slide is basically how I want you to write the hypotheses out for the most part. Write out each parameter all the way. In my null, I have one parameter equal to the other parameter. And in my alternative, I have one parameter greater than the other parameter. Write them out like that. And like I said, if you want to follow what I have as a template, I think that will work. Number 2, Beyond the Numbers 3.31 question 1, which is on page 324, although the hypotheses for the test you need to do and the sample data are on page 323. The test that you want the alternative to be that p is greater than 0.32, and then your sample proportion is the one for site 17, the one that's in bold, so your sample proportion is 0.45 with a sample size of 100. This problem's worth 2.5 points. 1 point for using the correct distribution to find the p-value, half a point for the mean and standard deviation specified on the right side, half a point for the correct cutoff, and half a point for the correct tail. So like left tail or right tail or both tails. That's what I mean by correct tail. That very last part in the wording about how there are two different ways to find the p-value, where you can find it using the test statistic and you can also find it without using the test statistic, that's because this has to do with a proportion where you have that option. And the next couple of slides illustrate the thing that I would want in each case. This example uses site number 1 instead of site number 17, but it's the same basic idea. This one here, this screenshot, I'm not using the test statistic. If you look at the mean and standard deviation, I've got the mean set up under the assumption that the null hypothesis is true, right? It's that value that's there in the null hypothesis. And then the standard deviation is based on that assumption as well, and I've got that rounded to 4 places. If you use this type of normal distribution to find the p-value, so if you don't compute the test statistic first, then this is how you would set it up, and then your cutoff is just going to be the sample proportion. The other option, which is to use the test statistic, which is realistically going to be the one that's more conventional, that looks like this screenshot, where if you're going to use the test statistic, your correct reference distribution should be a standard normal. If you look on the right side, I've got a mean of 0 and a standard deviation of 1, so I've got a standard normal distribution. And if you're going to use a standard normal to find the p-value, then the cutoff should be your test statistic, and that's the test statistic that you get if you use site number 1, 0.643. So that's the cutoff here. What you have to do for problem number 3 is pretty similar to what you have to do for problem number 2, where essentially you're just providing a stat key screenshot, and this is a hypothesis test for a mean instead of a proportion, and there's a different inequality, so those things are going to make some changes to what you have to do, but it's the same overall idea. The test statistic is already computed here, which means there's not really any algebra that you have to do leading up to going directly to stat key. And part A, worth 2.5 points, just like number 2, it'll be 1 point for using the correct distribution, half a point for having the correct degrees of freedom, half a point for using the correct cutoff, and then half a point for the correct tail or tails. And then part B, that's just half a point because it's either that the null should be rejected or the null should not be rejected. There's not really anything else you have to add to that. Number 4, part A, stating the null and alternative hypotheses and symbols, that's worth 2 points. Half a point for the correct parameter, half a point for the correct value on the opposite side of the equality or inequality, half a point for the correct inequality in the alternative hypothesis, and half a point for, I guess, the correct equals in the null. If you want to write the null with the appropriate non-strict inequality, that would also be fine. For B and C, ultimately there are 2 ways that you can make a wrong decision. Either the new assembly method takes less time on average, or it doesn't, and you could conclude the opposite statement. So B and C are the 2 ways of making an incorrect decision, a type 1 error and a type 2 error. One of those would be concluding that the average assembly time using the new method is less than 42.3 minutes when that is not the case. The other way of being wrong is not concluding that the average assembly time using the new method is less than 42.3 minutes when that is the case. Those are essentially the 2 answers that you want in some order. I guess you can phrase them a little bit differently if you want to. If you want to phrase the null as the average assembly time using the new method is 42.3 minutes, or the average assembly time using the new method is greater than or equal to 42.3 minutes, both of those would be fine. The main thing to watch out for is that it's easy to get the errors backwards, so make sure that doesn't happen. The other thing is make sure you get the context in there. If there's no context in B and C, there's no partial credit. That has to be there. Since they're only worth 1 point, that basically zeroes it out if the context is missing. Number 5, I suppose that first sentence ultimately is a conditional statement. If there's a hard Brexit, would you support Irish reunification? I guess that's really the way that that's ultimately phrased, and I just kind of rearranged it a little to make it shorter. But this is one where you don't have to do too much in R. It's really just going to be 1 line of code because prop.test will essentially do the entire thing for you. This is for a proportion, so there's no sample data that you have to retrieve out of a CSV file or anything like that. You've got the numerator and the denominator in the first sentence, and as far as the arguments for the test function, it's those 2 things, then specifying the null, specifying the direction of the inequality in the alternative, and then making sure that the continuity correction is turned off. if you follow along with the examples that we had the day before the last test, I think it will be pretty analogous between what you have to do here and what you had to do there. So again, this is really short. What you have in R should be a single line of input, so a single line of code, and then the output will be there where you've got your p-value in it along with a bunch of other stuff. And then part B, making a decision about the null and then including a formal conclusion. So if that's worth 1.5 points, it's going to be half a point for the decision and then 1 point for the formal conclusion. For number 6 and number 7, you have to retrieve the sample data from a CSV file. It's right next to the lab document on Canvas. It's called lambsandtree.csv. It looks like this if you open it up using Excel, where you have lambs in the first column, tree in the second column, and that tree column extends farther than row 32, but that's generally what it should look like. So you're using this sample data, not any kind of preloaded data that's already there in R where you just have to call it using the data function. There's none of that here. Question 6 involves the tree data, so the second column of that CSV file, where what we have here is that certain species of trees believed to have a lifespan of 135 years, and then we want to see if there's evidence based on that sample data that the 135 is incorrect and that it should be something else. So there's a sample of size 51, meaning that the CSV file should probably go down to row 52, considering that there's a header. And as far as putting this together is concerned, you do have to pull that sample data out of the CSV file, which is why if you look at the points down toward the bottom of the slide, half a point is for using the read.csv function correctly. Where you would put in the directory, do it just like we did it in class, where if you use file.choose with the empty parentheses, then that will give you a pop-up window, and then you can just conventionally go and pick the file the way you normally would. That way you don't have to worry about specifying the directory correctly. Then half a point for storing the tree column, because once you get the CSV file in there, it's essentially just as one big block. And you don't want the entire thing, you just want the tree data for this part. So the storage of the tree column, that would be the next thing. So I would probably just call it tree, and just remember that it's the second column, not the first. The first column, the lambs, you need that for number 7, so we'll get there, but you don't need it now. Then 2 points for part A, which is really just using the t.test function. And the arguments for that will be pretty straightforward. It's really just going to be whatever you called your sample data when you stored it in R, and then you have to specify what the null hypothesis is. And that's realistically about it, because the default is a two-sided alternative, and that's what you've got here. Then part B, making a decision about the null, that's just half a point. That part's just either you reject the null or you don't reject the null. No formal conclusion there. Number 7, once you've got the lamb data stored in R by itself, so presumably what you're going to do is you're going to use the read.csv function to get the CSV file in there, and then separate out the two columns, so the tree column and then the lambs column. The lambs column is shorter, so R will fill the rest of it with NA values so that the lengths of lambs and tree match, which is really just there as a default in case you're going to make a regression model, which is a thing we haven't covered yet. So if you want to get the NA values out of there, you can. NA.omit will do it, and that's there on the lab instruction sheet. You don't have to do that here. If you needed something like the mean of lambs or the standard deviation of lambs, then you would need it, because those functions won't compute with the NA values as part of that vector. But in order to get a histogram or in order to run the t.test function, it doesn't matter. If they're in there or if they're not in there, you're going to get the same thing. So NA.omit will clean up that sample data a little bit for you, but you don't have to do it here. Just like with number 6, it'll be half a point for the correct use of the read.csv function, which realistically you could do once rather than twice. You could just do it once and then do number 6 and then number 7 in succession, and then essentially the read.csv line would just count twice. And that's fine, there's nothing wrong with doing that. Then half a point for storing the lambs column, I guess just remembering that it's the first column, not the second. 1 point for part A, which is the histogram, 2 points for part B, which is the t.test part, and then half a point for part C, which is the decision. The histogram we went over in class with what happens. The function that you want is hist, H-I-S-T for histogram, and if you call your sample data lambs, it would be hist of lambs. And then a histogram will pop up in a window on the right side of the screen, and if you right-click on the histogram, one of the options is to copy it as a bitmap, which is a kind of picture, and then you can just copy it directly into a Word document. That's probably the easiest thing to do. The histogram that you will get, the default one, is on that slide. And you can make that look different if you want to change the colors, if you want to have the bars be a different color, or the outlines of the bars be a different color, or have it shade diagonally. You can do all those things, and that's there in one of those documents about using R that's on Canvas, but you don't have to. If your histogram looks exactly like the thing that's on this slide, that is perfectly fine, and that would be full credit. Then the next thing is to use the t.test function to do the hypothesis test to see if the mean weight of all female single birth Rambouillet lambs born in April is greater than whatever constant term you need to put in there based on what letter your last name starts with. So this is where there are going to be some differences, or different people are going to have different things, and some of the differences in the p-values that you'll get will be kind of drastic, which maybe you won't expect because it doesn't really look like those numbers are spaced that far apart, but that does happen. And then the last part, make a decision. That's just reject the null or don't reject the null.